Hello mathematicians, hope by this video and getting a little bit of practice you can see I can use lists or tree diagrams to determine the probability of compound events. We're going to look at two different examples and kind of two different ways that we can do this in this video. Let's start with our first example. So it asks, if you flip a coin 2 times, what is the probability you would flip a heads and a tails? So we can either make a list or draw a tree diagram to solve this. This one is fairly straightforward, so making a list might be okay in your head, but I think that a tree diagram might lead to a more accurate a process, and that'll allow you to make your list using a tree diagram. So let's just start here. So if we were to flip a coin 2 times, so let's say the first time we would get a heads. So these are the possible outcomes. So here would be our list. So let's say we rolled a So let's say we flipped a heads on the first coin. Then we could also flip a heads on the second coin. So we could get a heads and a heads, so H for heads. So we could get a heads and a heads, or we could flip a heads on the first coin and then a tails, T for tails, on the second coin. So those are two outcomes. So if we roll heads on the first one, these are the two outcomes. If we flip a tails on the first flip, then we could also flip a heads on the second flip. If we flip a tails on the first flip, we also could flip a tails on the second flip. So this would be all possible outcomes that could happen if we flip 2 coins, or flipped a coin twice, that is. So our favorable outcomes here. So we wanted to ask, what is the probability you would flip a heads and a tails? So this one is a heads and heads. So that does not count. So this set is not what we were looking for. Here we go. This is a heads and a tails. So that would be a favorable outcome right there. I'll just put a little box around it. This also is a tails and a heads, but order doesn't matter in this problem. It does not ask a heads and then a tails. It just says what is the probability you would flip a heads and a tails. So this one also works for this problem. That is a favorable outcome. And this one over here is a tails and a tails. So just remember, probability is equal to the favorable outcomes over the possible outcomes. So in this case, we have 2 favorable outcomes, and there were 4 possible outcomes. So the probability here is equal to 2 over 4, which, well, we can simplify that fraction. That'd be 1 over 2. All right, so 1 over 2 as a fraction, which is 0.5 as a decimal, and 50% as a percentage. So the probability, we could either write it as a fraction, a decimal, or a percentage. So it'd be 50%, 0.5, or 1/2. Another way that we could do this is we could make a tree diagram. Let's just do a quick example of how to make a tree diagram. So tree diagrams, they can either go left to right or top to bottom. I think typically most people move left to right. So our possible outcomes on the first one would be heads and a tails. So we would label this first flip. So the first flip, we could get a heads and then a tails. Now on our second flip, we could go and we could get a heads. So we kind of connect these two, and then we could get a tails here, and then we connect these two, and then we could get a heads and then a tails. So going from tails, we could go tails then heads, and then a tails, then a tails. So we can see this tree diagram represents what we call the sample space. So this would be the sample space for this problem right here. So we could go in now, and we could go and let's just circle the favorable outcomes. So we could kind of follow this line here, this tree, to find the favorable outcomes. So we want a heads and a tails. So we could go from heads to heads, which is not what we want. We want a heads and a tails. Or we could go heads to tails. Okay, well, that's what we want. So I'm going to go ahead. I'm just going to circle that route on the tree diagram right there. So we want a heads and a tails, or we could go tails then a heads. So this also would be a favorable outcome. And a tails and a tails. Well, that is not a favorable outcome. So once again, there's 2 favorable outcomes with 1, 2, 3, 4 possible outcomes. So again, this would be the exact same. So we'd get 1/2 or 0.5 or 50% using a tree diagram. So this is just maybe a way to visualize what is going on, and you can actually use this to make a list if you prefer that method. Let's look at another little bit more complex example. So this one's a little bit of a personal example here. It says Mr. Knudsen has 2 belts, brown and black, 2 pairs of shoes, brown and black, and 4 shirts, blue, red, green, and yellow. And I actually do not have a red, green, or a yellow shirt, but just for this problem, I just put that down. I thought it might be a little bit easier. And it says, what is the probability that he will wear a brown belt, brown shoes, and blue shirt? And this problem is assuming that I'm just randomly choosing different shoes, belts, and shirts, and don't care about how they look with each other. It's just I'm just randomly choosing one belt, 1 pair of shoes, and 1 shirt. So what is the probability I would wear a brown belt, brown shoes, and a blue shirt? So I'm going to suggest that we make a tree diagram to represent the sample space of what is going on in this problem. So let's start. So there are belts that I can choose from. So that'll be the first layer of this tree diagram. There are shoes and there are shirts. So there are 2 colors of belts. There are brown and black. So I will go brown. So I'll go BR for brown, brown, and black. And I'll go BL for black. And there are 2 pairs of shoes. So from brown, I could go to brown shoes, so BR here, and I'll go BL, so black shoes. So I go from brown belt, brown shoes, brown belt, black shoes. All right. And I'll do the same thing down here. So I go brown shoes and black shoes there. So now I'm going to go ahead and I'm going to draw my connections on this tree diagram right here. And now for each pair of shoes, I'm going to have 4 pairs of shirts that I can use. So for each one of these, I'm going to have 4. So I'm going to move this up a little bit just to save myself a little bit of space. So I could wear a blue shirt, a red shirt, a green shirt, and a yellow shirt. So these would be the 4 outcomes for this right here. And I'm going to connect all my points right here on this tree diagram. And I'm going to repeat these 4 things for all 4 of these outcomes. So again, I go blue, red, green, and yellow. And again, I would draw my connections here and repeat the process again. So blue, red, green, and yellow. And one more time. Blue, red, green, and yellow. So now I've got my sample space right here. So now I just need to go in and use this sample space to calculate what the probability is. So what is the probability I will wear a brown belt, brown shoes, and a blue shirt? So brown belt, so it'd be right here. Brown belt. Brown shoes is what we're looking for. And a blue shirt. So be this first rung right here is what this problem is asking for. So I'm going to go ahead and circle that right there. And there are no other favorable outcomes right here because this is a brown belt, brown shoes, red, brown belt, brown shoes, green, brown belt, brown shoes, yellow. So none of those fit what is going on. And if once we move down here, we have brown belt and a black shoe. So immediately right there, that does not fit the criteria because we're looking for a brown belt and brown shoes. So this is a brown belt, black shoes. So that's not good. Black shoes immediately, that is not what we're looking for. So this is the only favorable outcome, this top tier right here. So our probability would be equal to there's only one favorable outcome, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16 possible outcomes. So it'd be 1 out of 16. So the probability I would wear a brown belt, brown shoes, and a blue shirt would be 1 out of 16 as a fraction. Let's convert this to a decimal really quick. This would be 1 out of 16. 16 does not go into 1, so we draw a 0 there, add an extra 0. 16 doesn't go into 10, 1 more. 16 goes into 100. 6 times 16, so let's think 6 times 10 is 60. 6 times 6 is 36. So add those together. 60 plus 36, we get 96. 100 minus 96, that's going to give us 4. Add an extra 0, bring that down. 16 goes into 40 twice without going over. 2 times 16, again, 2 times 10 is 20. 2 times 6 is 12. 20 plus 12 is 32. 40 minus 32 gives us 8. Add an extra 0. Bring the remainder down. We get 80. And 16 goes into 85 times. And it goes in there evenly, so we get no remainder and we're done. So it'd be 0.0625 as a decimal. So if we move this to a percentage, move it over 2 places, so it'd be 6.25 as a percentage. So that was it for our video. We gave one simple example of how to draw a sample space and create a list, and we gave one a little bit more complex example. So I hope after watching this and getting a little bit of practice, you can say, I can use lists or tree diagrams to determine the probability of compound events.